Hey everybody, Miss Butler here. Today's video is on mass spectroscopy, which connects average atomic mass and isotopes, and then these graphs that we're going to be able to analyze to figure out more information about the isotopes. Alright, so for this video, you're actually going to do this mass spectrograph worksheet with me. So there'll be times in the video where I ask you to set a timer and try some of the problems, and then we'll go over the answers. Please actually do that. It will make your learning much more thorough, I guess, instead of just going through the motions. So looking at the worksheet, the introduction says, mass spectrometry was developed in the search for the discovery of isotopes almost 100 years ago and has evolved into an incredibly powerful tool for analyzing the mass and structure of compounds. It is widely used in laboratories all across the world for forensic analysis of trace amounts of substances and also in research to determine the structures of large and complex natural products such as proteins and nucleic acids. I used a lot of this in college during organic chemistry and advanced organic chemistry as well. So you will definitely see this in college if you take any sort of science class, chemistry class, biochemistry, anything like that. Okay, let's start with a warm-up. It says use the atomic masses from the periodic table to answer the following questions. The first three require no calculations, just logical thinking. So no calculators, you're not actually calculating, you're just going to find these elements on your periodic table, and we're going to use some common sense. So I would like you to set a timer for, let's do 3 minutes, 1 minute per problem, 3 minutes. And when the timer goes off, you can resume this video, but I want you to try the warm-ups 1, 2, and 3. Set your 3-minute timer now. All right, 3-minute timer is up. Let's check out the answers. All right, so the first one, we have indium, the isotope indium-113 and indium-115, and they actually gave you the masses of those individual isotopes. What do you think is more abundant? And I said indium-115. The reason is because on the periodic table, indium has an average atomic mass of 114.82 AMU, which is much closer to the mass of indium-115 than it is the mass of indium-113. So what that means is there are more indium-115. It is more abundant than indium-113. It has more say in what the weighted average is, that average atomic mass on the periodic table. Let's look at number 2. Silver has 2 stable isotopes, silver 107 and 109, which describes the relative proportions of the 2 isotopes. I said slightly more of one than the other because there must be slightly more of silver 107 because on the periodic table, the average atomic mass is 107.87, which is a little closer to the relative mass of silver 107 than silver 109. So it's slightly closer, which means we have slightly more of silver 107 than silver 109. And lastly, 3 stable isotopes for oxygen, oxygen 16, oxygen 17, and oxygen 18, which describes the relative proportions, and I said almost entirely one, very little of the others, because on the periodic table, oxygen has an average atomic mass of 15.9994 AMU, which is almost nearly the mass that was given for oxygen 16, 15.995. So that's almost exactly the same, which means oxygen must be almost all oxygen 16, and only a tiny, tiny percentage of the oxygen isotopes are oxygen 17 and oxygen 18. All right, this says below is a schematic diagram of a mass spectrometer, the machine used to separate an element into its isotopes and to determine the isotopic composition. Below the diagram in random order are the descriptions of the steps involved in the process. Match each step to the part of the machine where the steps takes place. So these steps down here are in a random order. You're going to match the letter based off the picture. So you'll read the description. A series of negatively charged rings accelerates the positively charged ions. And so if you think, for example, that is letter A, you'll put an A right there. Again, they're in random order. Couple of things. Oops, I meant to put these guys, sorry. It's kind of hard to read on your worksheet the way it copied. So these guys here all have negative charges on them. This plate down here is positive and this plate up here is negative. So I want you to set a timer. Let's do 2 minutes to try to label these guys. Don't worry about this question down here or the exercise yet. All right, your time is up. All right, I'm going to go through this diagram in order. So the first thing that happens at letter A is a sample of the element is heated to vaporize it. So this is an element with all of the isotopes part of it. It's heated to vaporize it, converting it into individual gaseous atoms. So I'm heating up this sample X right here. Then we move on to letter B, where a high voltage electric current is passed through those gaseous atoms. So here's my electric current going through these atoms that are now a gas. Letter C is that this electric current knocks electrons off the atoms and changes them into positively charged ions. So at letter C, we now have positively charged ions. Letter D, a series of negatively charged rings accelerates the positively charged ions because opposites attract. So these positive ions are going through these negative rings. We move on to letter E. The beam of ions is passed through two rotating discs with staggered slits. This part of the machine allows only ions with certain velocity to make it through. So as you can see, there's these rotating rings with little slits in them. The positively charged ions make it through, but some of them are deflected and stuck because they don't make it through the slits. So only certain speed ions can make it through depending on how the speed of these rotating rings. Okay? Now we move on to letter F. The beam that made it through these slits, so there's still ions, passes through two oppositely charged plates. So we have a positive charge down here and a negative charge down here. So it's passing through these oppositely charged plates. Letter G, the ions are deflected towards the negative plate because we know that these positively charged ions like the negative charge, right? So they're avoiding the positive, they're moving towards the negative. So these ions are deflected towards the negative plate. The lighter ones, so the ones that came from the lighter isotopes, get deflected more and hit the plate sooner. So the lighter ones take a sharper turn because it's easier for them to and turn towards the negative. And the heavier ones have more momentum, and so they hit the plate farther down. So they are slowly boom, 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 deflected towards the plate. Okay? And then letter H, the particle detectors keep count and translate the information into a bar graph known as a mass spectrum, and it shows the isotope masses on the x-axis. So here's the isotope masses. I know it's a little blurry, but this says 67, this says 70, and 72. So you can see that as these guys hit, we get a nice bar graph for the mass of 67, a nice bar graph for the mass of 70, and a little bar graph here for 72. The relative percentage is on the y-axis. So these are the percentage of particles or ions that are hitting the plate. All right, now that we know how this machine works, let's check out the follow-up question. According to the mass spectrum shown above, what are the three isotopes of X and what are their corresponding percent abundances? So I'm just going to give this to you guys because I know your graph is kind of small and blurry. So first of all, I said that the isotope X, the first one was 67, the second one was 70, and then the other one had a mass number of 72. And then I'm looking at this bar graph to get the percent. And I know there's some eyeballing, so let's go with 30% for isotope 67, 56%, and 14%. Those should add up to 100% of the isotopes. So here's what the exercises look like. For the following problems, show all work. Based off your reading of the element X in problem 4, so we got our percentages here, make an approximation of the average atomic weight. So my guess was, because we have like 56% is 70, right? A little bit less, 67, 72. My guess was it's maybe around 69 AMU. Right? Because we know most of it's around 70. There's a significant pull down towards 67, so maybe a little less than 70, and just a tiny bit above 70. So my guess was 69 AMU. Let's now actually calculate it after we took our educated guess. So we are going to use our isotope formula. So we take the percent in decimal form, 0.30, okay, times the mass number 67, plus 0.56 times the mass number 70, and then 0.14 for the 14% times the mass number 72. So we multiply, add, multiply, add, multiply, and I got an average atomic mass for this unknown element as 69.38 grams per mole. So I used the graph to get the percentages and the mass numbers so I could do my average atomic mass calculation. All right, on the next page of your packet, you have 3 more of these problems that I want you to try. For all 3 of them, you have to predict without looking at the periodic table and without calculating. So just looking at either the graph or the numbers provided, you need to predict what the average atomic mass would be, and then you're going to actually calculate it. So for number 6, you're going to go off of the graph. So you'll get your mass number and you'll get your percentages. For number 7 and 8, I give you the percentages and the mass numbers, and you need to calculate and then make the graph for me. What should the graph look like? That should do it. How about we do 5 minutes on the timer, 5 minutes to do questions 6, 7, and 8. So set a timer on your phone for 5 minutes. All right, your 5 minutes is up. Here are the answers. All right, no worries if your percentages were slightly off of mine because we are eyeballing it, but I said 94% and 6% for isotope 39 and 41 respectively. Based off just looking at this, I estimated that we're going to be really close to 39, maybe slightly higher, so I did 39.2. Okay, when I calculate, I take my percent in decimal form times the mass, my percent in decimal form times the mass, and add those 2 components. So I got an average atomic mass of 39.12 grams per mole, or AMU is fine. On this guy, they give me the numbers and the percentages. So I took an estimate based off these mass values and percentages of about 20 grams per mole. I sketched my graph. So the mass of 20 had almost just over 90%. The mass of 21 had less than 1%. So tiny, tiny little peak right there. And then the mass of neon 22 had just under 10%. So you can see my little peak there. And so I calculated the same way, percent in decimal form times the mass number, percent in decimal form times the mass, percent in decimal form times the mass, added up all of those pieces, and got neon's average atomic mass. Finally, we have arsenic. This one, arsenic only has 1 isotope, so 100% of arsenic has a mass of 74.922. So I drew my 1 peak all the way up to 100 at that mass of 74.922, almost 75. And we're just going to take 100% times that, so we know that the average atomic mass is the same as the weight of this 1 isotope. Let's take another 2 minutes to try question 9 and 10. So set your timer for 2 minutes. You can label your axes. This is percent abundance. This is isotope masses. So again, 2-minute timer to do 9 and 10. All right, your 2 minutes are up. Check out number 9. Hopefully you were able to figure out that the remaining percentage was 0.62. Remember, the percents of all the isotopes have to add up to 100%. So if I add up all of these percentages and then subtract from 100, that's how I got my remaining 0.62%. I made my mass spectrum. I calculated my average atomic mass for zinc, and I did also a prediction before I started. Okay, number 10, earlier this year you categorized substances as being elements, compounds, or mixtures. Is it possible for something to be a pure element and a mixture at the same time? So truthfully, a pure element is made of a mixture of isotopes, right? A pure element means 1 capital letter from the periodic table, but most elements on the periodic table have multiple isotopes, but it is technically the same element. It's just that we have these isotopes, meaning same number of protons, different number of neutrons, which means they have different mass numbers. Are any of the elements on the worksheet not mixtures or mixtures of isotopes? I said number 8 only has 1 isotope, right? There was only 1 line on my bar graph. So a compound, and then is it possible for something to be a pure compound and a mixture? Well, a compound can form from various isotopes of 2 or more elements. So for example, CH4 could be made of carbon-12 or the isotope carbon-13 bonded with those hydrogens. So technically, you can make CH4 and a molecule might have the carbon-12 isotope or the carbon-13 isotope. Isotopes do not act differently in terms of chemical reactions. They do act differently in terms of nuclear reactions because those involve the nucleus, which is different between the isotopes. All right, I really like the packet we just completed, but there's a couple other things related to mass spectrometry that are not in the packet. So if you want to just turn your packet over and take some notes on these last couple of slides, that would be awesome. So here's this, read this. The key to mass spectrometry is that all of the particles go into the deflection chamber with the same kinetic energy. They do not, however, have the same mass to charge ratio, M to Z. Although most of the ions formed are +1 ions, their masses are different. That's what makes them isotopes. Therefore, the amount of deflection they experience by the electromagnet is different. So they're all going through those plates with the same speed, but because they have a different mass to charge ratio, they are able to be deflected quickly, or if they're nice and slow and big, they will be, so I should say, if they're large, they'll be deflected slowly. The strength of the electromagnet can be varied, so only particles with a particular mass to charge ratio can make it to the detector. Other particles collide with the metallic slats of the instrument. They are neutralized and then removed by a vacuum pump. The machine is calibrated using carbon-12 isotopes, which are, by definition, exactly 12 AMU. Okay, number 6, consider the following ions formed in a mass spectrometer. Rank the ions in terms of their degree of deflection by the electromagnet from least to greatest. Greater deflection means a tighter turn towards the negative pole of the electromagnet. Make sure all group members are able to explain. Okay, so it might be kind of small on the screen, so I rewrote. This is the mass number in the upper left, and this is the charge. Let's figure out the mass to charge ratios. So for this guy, the mass to charge ratio is 19 over +1, 16 over +1, and 17 over +1. So the smallest charge to mass ratio will have the highest degree of deflection. So this guy is going to be the highest degree of deflection. It is going to make the tightest turn. And the largest mass to charge ratio will have the lowest degree of deflection. Easy enough. All right, here's another read this. The mass spectra you have been looking at in this activity, and the one we did as well, use percent abundance on the y-axis, right? So they gave us the percentages, super easy. Typically, however, the spectra use relative intensity. So we need to learn what this is. This is very important. So this is kind of the high school version of the mass spectra, but what really is given when you do this in a lab is called relative intensity. The ions from the sample are sorted by mass to charge ratio by the mass spectrometer. The ion that hits the detector the most is assigned a relative intensity of 100. So what this tells me is that the ion with the mass of 24 hit the detector the most, so it automatically is assigned 100. The other ions, so these two ions, are given proportional relative intensities based off their abundance compared to this guy at 100. So let's look. So here's my percentages for magnesium. 79% were mass number 24, 10% 25, 11% 26. Here's what I see. Out of these, there were 100 plus 13 plus 14. So there were 127 atoms detected. Think of it that way. So for magnesium, 24, 100 out of the 127 were magnesium 24. And I'll times that by 100 to make it a percent. 79% were magnesium. Magnesium 25, 13 out of the 127 total were magnesium 25, which is 10%. And for the magnesium 26, 14 out of the 127 were that isotope, so that's the 11%. And so what you can see is when we are given relative intensities on the y-axis, you add up the total and you need to find the percentages yourself. Not very hard, but the hard part for AP Chem students is paying attention to the axes label and just not forgetting that if it's not in percent, then we need to total up the numbers for the relative intensities and find the percentages ourselves before we calculate average atomic mass. All right, so the mass spectra we just looked at, the sum of all the percent abundances are equal to 100. That is reasonable because all of the isotopes of magnesium are present in the sample, so it should add up to 100%. The sum of the relative intensities does not equal 100. It equaled 127. Well, the reason they don't equal 100 is because, remember, the way the relative intensity graph works is that the most common isotope is assigned the intensity of 100. Okay, and then theoretically, how many magnesium ions were detected? We already added that up, 127. And then this is just finding the percentages. So 100 were magnesium, 24 out of the total 127 times 100. That's how we got the 79%. Same thing with the 13 peak. So 13 out of 127 is how we got the 10% for the magnesium 25. All right, last slide and last topic. This is the most common use of mass spec in organic chemistry. So mass spec is also used to study large organic molecules. Organic molecules are carbon-based molecules. When a sample of a pure compound is analyzed in the instrument, some of the molecules get ionized whole, molecular ions, while some are fragmented and ionized. The fragmentation occurs in predictable patterns, allowing scientists to propose a chemical structure for unknown substances. Consider the mass spectrum for pentane. So these are carbon bonded to 3 hydrogen, bonded to another carbon with 2 hydrogen, bonded to another carbon with 2 hydrogen, bonded to another carbon with 2 hydrogen, bonded to another carbon with 3 hydrogen. So this is like a chain of carbons, all with hydrogens hanging off. Match the molecular ion fragment ions below for each of the lettered peaks. So what we see is we have relative intensity and we have the masses here. These are all the different fragments. So if I took this guy, right, and I just took off one little fragment, we can see this guy here. If I take off 2 fragments or 3 fragments, right? So essentially, we are just, some of these pieces make it through whole, and some of them are broken off into smaller pieces. What we're going to do is we're going to match these based off the molar mass. So if you add up the molar mass for this guy, you should get 72 grams per mole, which means this peak right here, letter E, is the amount of pieces that made it through whole. If we find the molar mass of this smallest peak, we get 15 grams per mole, which is going to be this guy right here, letter A. So you can see they just go in order based off molar mass, but you can see letter C, the middle one, that was the most prevalent or most intense, meaning most of the fragments got essentially broken nearly in half or close to half. And then finally, peak cluster A has a small peak at 14, right? So one little peak here. What may have fallen off the CH3 plus ion? So this guy we said is letter A. What may have fallen off to give us a small little peak of particles that have a mass of 1 less? Well, we know hydrogen has a mass of 1, so it's possible that this is actually a little CH2 because one of the hydrogens fell off, right? So these little peaks are just when we've added or lost a little extra hydrogen. Okay, but for the most part, you can see that there's 1, 2, 3, 4, 5 distinct sections, 5 distinct fragments, minus some of these maybe little guys that have lost or gained some extra hydrogens. Cool? All right, that's mass spec for you. If you have done M&MEM lab, you can now do the mass spec questions related to the M&MEM lab. If you're like, M&MEM what, Miss Butler? Don't worry, you're going to do that lab in class next, and you'll be able to do all of the questions now that you know about mass spec. See you in class.